Alright, making a video. Draft science and such. Physics. Yale guy. Let's see, Yale. So, I've meant to do, I don't know whether I have in the past, but I'm going to do it again if I have. But this, look, we got the MIT guy, we got this guy. Now, if somebody can find Stanford guy, whatever his name is, doing the two-slit experiment, video where he explains it, I'd be curious just to see how wrong he gets it too. And this is really, like I said, this is quantum mechanics, the key experiments in wave-particle duality. So he's using this as a, this is why we think the way we think. This is their explanation, their defense, their justification, their foundation for their understanding. And they don't accurately describe the experiment. I mean, it's a simple experiment and they don't accurately describe it. They don't, let alone interpret it properly. They can't even describe the experiment properly. Now, that's pretty bad when it's such a simple experiment involving so few moving parts and so few manipulations. There's very few presumptions. You have to have, there's not a ton of mirrors and the smoke and mirrors of technology. There's not devices that are measuring this and doing that, where you have to make all kinds of assumptions about how the device is working. This is a really simple experiment, and they can't, for the life of them, describe it accurately ever. And these are professors teaching the subject. And you people are okay with that. You think that's the way physics should be done. This is the way it should work. Frankly, I mean, all you can do is say this is it's appalling. If it was any other subject, if it was driver ed, you would find it offensive and wrong if they were saying things this inaccurate. They were describing the rules of the road inaccurately, or how fast a car can slow down inaccurately, or what you can do. Well, anyway, I suppose because that would have some sort of consequence. So it really just matters whether somebody can drive into your living room with their mistakes rather than anything else. And I don't know, this love affair with sloppy authority should bother somebody. Alright, anyway, so let's play the video. And
given the information they had, they built
terrible.
The best theory that they could. And if you give me more additional information, more refined measurements, something to the 10th decimal place, I may have to change what I do. That's how it's going to be. So
right, and you don't, there's other circumstances, so he's just saying, yes, okay, well, until something better comes along. But it's sometimes you don't need more experiments, you just need to be more careful in how you're analyzing the experiments you have. And clearly here, a little more caution would make it obvious your explanation is, at minimum, grotesquely incomplete. Grotesquely so.
that's always going to be, for example, in the big collider, people are expecting to see new stuff. Hopefully stuff that hasn't been explained by any existing theory. And we all want that because we want some excitement, we want to find out new things. The best way not to worry about your old theories is to not do any experiments. Then you can go home. But that's not how it goes.
I'm just seeing if there was a date on this. It was uploaded in 2011. I just was wondering when it was made, and it doesn't say that, so we'll just have to move along.
More and more stuff. So here's what you do to find out what's wrong with electrodynamics. I mean, with Maxwell's theory.
So he's saying what's wrong with Maxwell, because Maxwell basically considered everything a wave, and he's basically going to argue for particle elements here by using the two-slit experiment as an example, which is ironic, because they just go into the analysis of the experiment by calling everything a wave anyway. So what's the point? I mean, there really isn't much point. And it's really not about Maxwell's equations being wrong. It's about what you interpret the causes to be. And yes, the cause isn't a wave function. The cause is a frequency that particles come at.
It all starts with a double-slit experiment. And you have this famous double slit. and some waves are coming from here.
All right, see, so they always start with that as the assumption. Oh, there's waves coming in from here. So they talk as if this is, again, so he's almost talking as if it's an argument against wave theory because of the way the photons end up arriving as a clump. And so this is kind of ironic that he forces the photons to be a wave before they even get to the slits. So he's already assumed this.
We have some wavelength lambda.
We have a distance between events. Yes. Not necessarily a wavelength, a distance between particles. Could be said exactly the same way, says something entirely different, doesn't it? Distance between bullets.
Then in the back, I'm going to put a photographic plate that we want some excitement, we want to find out new things. The best way not to worry about your old theories is to not do any experiments. Then you can go home. But that's not how it goes. You probe more and more stuff. So here's what you do to find out what's wrong with electrodynamics, with Maxwell's theory. So it all starts with the double slit experiment, and you have this famous double slit, and some waves are coming from here.
The audio is out of sync, which I didn't notice before, but whatever.
You have some wavelength lambda. Then in the back, I'm going to put a photographic plate that we want some excitement, we want to find out new things. The best way not to worry about your old theory.
How is it doing? Why is it fucking up like this, YouTube? You son of a bastard fucker, fucker. Alright, I'll try restarting it from a new position.
What you will find is that the region in front of it got pretty dark, or let's say had an image, whereas if you go too far from the slit, you don't see anything. So that's called intensity.
Alright, so he's saying, okay, you have this slit's blocked now, so this slit's open, and this is what you get. So we got the typical lie. This isn't what happens. Single slit diffraction is a known since Newton's. It's Newton's rings, okay? Any small aperture maximizes diffraction by a simple principle, right? More surface. The smaller I make a hole, the percentage of space, open space to surface space, gets smaller and smaller, however you want to describe that. But it becomes more likely that something is going to interact with the surface the smaller I make the hole. Okay, and you'd end up with a ringed pattern if it was a circle, which is lines when you make it a slit. So even in Newton's time, it was known there were on, off with an aperture. So there's nothing here that's accurate. This isn't what light does. So he's describing this as light. He's not talking about water. He's talking about light. Photographic plate. He's talking about light, photons. And this is just, frankly, unacceptable, right? That's not the pattern you're going to get. And the bigger you make this slit, the more the pattern will look like this. So if I make this slit the same size as this, okay, I'll get a pattern that will be this bar, and this bar, and I won't see much else. I just see those 3 or 4, maybe 5 bars. That's all I'll see. So it's just going to be a big lump, and a big lump. It's not going to be very interesting. But if I make this slit, the single slit, as big as both of these slits, alright, then I'll get this. I'll get a full bar pattern, a strong center, and complete bars, maybe 12 or 15 of them, 16, and that's what I'll get. You know, no, this is a lie. It's not the truth. It's not anywhere close to the truth. It's not what light does. So why is he explaining it wrong? Why isn't he telling the truth? Because the truth is he can't explain the truth. That's why. If he pointed out that this is single slit diffraction creates an interference pattern. that the diffraction pattern looks like an interference pattern. That's what Newton's rings are. It's a diffraction pattern, yet if you make it lateral, it'll look just like an interference pattern. And that's their problem. And then they have to come up with some kind of Huygens nonsense or whatever to fix that. A principle they can't apply anywhere else in physics.
One is open. Then you close that guy, then you get similar pattern. Then you open both.
Right. So we know this isn't true. So we know this experiment hasn't been done. We know there's no opened one and then we closed another one and we got round and we got round. We know that doesn't happen. We know you're going to get interference pattern. It's going to be changed based on the distance of this barrier between the two slits. And but that's the truth. And we know if these openings are wide enough, you're going to get a very detailed pattern.
Then I told you, you may expect that, but what you get instead, let's see, I got to pick my graph properly, is something that looks like this.
Not exactly brilliantly done. And that part is semi-true. But what you actually get is something that looks like this. It's a fact that the double slit pattern falls inside of the single slit pattern. So these little lumps here. So the single slit at a narrow opening is the same pattern, the same shape of pattern that this double slit will be inside of. So there'll be, say, 16 little things in here, and there'll only be 7 over here, and then I drew it even smaller, but it'd be like, say you had 16 bars in the center, and you'll have like 8 bars in this one, and then you'll have 4 bars over here. So it'll diminish in intensity by how many bars will be in there, but and the center will still be much stronger than the fringes, these fringes, but it'll be 2 patterns superimposed on each other. There'll be a pattern inside a pattern. Where's the pattern inside the pattern? Again, it's just grotesquely inaccurate. This isn't the pattern. This sloppy crap isn't the pattern produced. And you can only see it that way if you control these sizes specifically to narrow the view. So if I make this opening very small, what happens is this spreads out. So as I make the opening smaller and smaller, this pattern spreads out and gets weaker and weaker because you're fanning it over a much larger surface area. So this pattern gets incredibly weak, and you don't see all of these bars anymore, and all you see is this. So what they're doing is, by making the slits a certain distance, they're basically annihilating these flanges when they want to. I mean, when they don't want them to be part of their experiment. And all they're really considering is this little section here, because that's the only section that's going to be visible. So if I make this slit narrow enough, I'll spread the pattern wide enough where all I'll see is one tiny piece of it. But the truth is, any physicist should know that that's completely arbitrary. That's completely dependent on how wide I make those slits. And all I do is double the width, and I will increase the pattern tremendously. Much more visible pattern will be produced. But this is stuff they have to know. This guy has to know there's a thing called single slit diffraction, and that the diffraction pattern is identical in the sense of its on-off-on-offness to what they're calling the interference pattern. He even says it's always recognized as an interference pattern. Well, why don't you call it that in the single slit experiment then?
Now that is the phenomenon of interference which we studied last time. So what's the part that's funny? What's the part that makes you wonder is if you go to some location like this, go to a location like this, this used to be a bright location when one slit was open. It's all...
Well, it's not by your drawing. This was totally inaccurate, so obviously it wasn't a bright location necessarily. But the truth is it could have been, okay, if there's some way for you to open and close slits that doesn't change the electrodynamics of the fields in the openings, which you may or may not be able to do. Now, there's no experiment. There's an experiment I've seen where they move a barrier across the two slits, but what we don't get as data is in the imagery. We don't have them superimposed on each other, so we can't see whether the lows meet the lows for the two single slitted patterns.
So bright location, reasonably bright when the other slit was open. But when both are open, it becomes dark.
So that's his claim. He's claiming that if you could really do that experiment, I opened one and then everything else stayed exactly the same. I didn't change the light source. I didn't change anything else. Didn't move it to the center here. Didn't change anything else. All I did was block this. And there's a dark spot at this location. And then I open this, a light spot. And then I open this and it goes dark. Now, if you could demonstrate that with an experiment, then maybe you could say it. But there's no experiment. Show it me. Show me the experiment that does that. That can somehow mechanically actually do that. Open or close a slit. Because that's what it's going to require. Because again, anything going across the surface is going to create a second edge for diffraction. So it's going to mess up your results. There's going to be more than one diffraction.
You can ask, how can it be that I open two windows, the room gets darker? Why doesn't it happen there and why does it happen here? The answer is that...
Well, the answer is it didn't happen. Number one, you don't have an experiment. So you can say this is what happens, but you don't have an experiment to justify that claim. And in this experiment, the way you've described it, you haven't described it accurately. You claim the single slit does this, when there's clear evidence the single slit does do this. So there already are dark spots in the single slit pattern. And all you're claiming is that the dark spots might move. Well, the moving of the dark spots a lot less of a mystery than the creation of a spot that is... my argument would be, his head's in the way in the moment, but if the two slits, the thing that might have an effect is the mass of whatever's in between the two slits. Obviously this is, if you think of this as electrodynamics, that's the subject. That's what this was originally called. Before quantum mechanics it was electrodynamics. And what you're going to do is change the electrical potential between these bodies when you put a barrier. When this barrier is filled, then this mass has a different electrical potential at the other opening. When you have, it's like having two spark gaps open. It's going to change the electrical potential than having one open. And obviously that can affect both photons and electrons traveling. It affects the photons because it affects the electrons and the existing ones between the two bodies. So obviously electrons are going to be affected by electrical potential of the material you're using as a slit, and the separation of the materials from each other, it creates an electrical charge between the two things, have a potential difference, and that potential difference is realized by an electric field.
You're sending light of definite wavelength, and the wave function psi, whatever measures the oscillation, maybe electric field, magnetic field, obeys the superposition principle. And when two slits are open, what you're supposed to add is the electric field, not the intensity.
Well, regardless, obviously I would contend that that's another presumption, that there's an electric field of a photon. There is no such thing. Or a magnetic field. Neither one of those things can be proven by anything but the very experiment you're using to claim them. And you're not describing it accurately, so why would one assume you understood what a photon was when you can't accurately describe a simple experiment, one that just can't be any simpler, two slits and a target, and you can't accurately describe the what happens. And then you're going to tell me there's something called a squiggly line thingy, electrical potential of a photon. No, there isn't.
Intensity is proportional to the square of the electric field. You don't add E squared, you add E. E is what obeys the wave equation. E1 is a solution, E2 is a solution, E1 plus E2 is a solution.
Yeah, well, again, he just jumped way ahead of his own subject, and then he'll go backwards and then go forward again, but that's way ahead of this experiment. Because now he's talking really that wave is just a probability wave, so there's no point in him talking about that.
No one tells you that if you add the two sources, I1 plus I2 is going to be the final answer. The correct answer is to find E1 plus E2, and then square that. But when you do E1 plus E2, since E1 and E2 are not necessarily positive definite, when you add them, sometimes they can add in the same sense, sometimes they can add with opposite signs, and sometimes in between, so you get this pattern. So we're not surprised.
Yeah, again, but that's, well, anyway, I'm just saying now he's a step behind, because now he already knows that he's going to point out that single photons do the same thing, so there is no adding and subtracting of photons.
And I told you many times why we don't see it when we open big windows. First of all, when you open a window, the slit size are all many million times bigger than the wavelength of light. Plus the light is not just one color, and so on. So you don't pick up the
the real reason is quite obvious, yes, is that the surface is the surface area is tiny compared to the volume of the opening. And that's all that matters, the proportions of opening to surface. So obviously as the aperture gets smaller, there's more surface, and so you're more likely to be within a millimeter of the surface. The likelihood of being within a millimeter of the surface is really big when the hole's this big, and really small when it's a window.
These oscillations are very fine. I draw them this way so you can see them. In a real life thing, if this were really windows and this was the back wall of your house, the oscillations will be so tightly spaced, I'll just draw some of them, that the human eye cannot detect the oscillations. It will only pick up.
Well, and it would only be a tiny percentage of the light that came through that would be oscillating. So it's, again, wrong for him to imply that all of the light is oscillating. Because the simple truth is, the light that goes through the middle of your window, it's not oscillating. It's not interfering. It's not doing any of that crap. It's going straight through your fucking window. And the only light that's getting affected is the fringe light, the light on the edges. I think it's just game over. That is just nonsense. Okay, to think that the light going through the center of the window is somehow interfering with itself. You're just dreaming.
The average value will in fact look.
Look, the truth is the probability is entirely determined. When they talk about a probability, all the probability is, it starts at the slits. And all you're really determining is the probability of the photon going here versus the probability of the photon going here. If the photon goes here, it diffracts. If it goes here, it goes forward. Or diffracts very little, depending on how close it is. The closer to the surface, the more you diffract. So it's decided here what's going to happen to the photons. And that's why, as you make the slit smaller, the pattern gets wider. Because you're creating more surface events. So as I cut this middle out, by making the slit smaller and smaller and smaller, all I'm doing is cutting out the stuff that goes straight through. And I'm maximizing the stuff that doesn't. And that's why the pattern gets wider. As the slit gets smaller, the pattern gets wider. And it's obvious that it's the surfaces that are causing the phenomenon. It's the probability of the photon going next to the surface that is the only probability involved. There's no probability anywhere else in here except did the photon go close to the surface or far from the surface. That's it. Nothing else to see here. that decides where the photon goes. And the day they can aim photons well enough to shoot them right at the edge is the day they'll find out that's why they diffract, and that's why they create this pattern.
Like I1 plus I2. So this is all very nice. This is how Young discovered that light is a wave by doing the interference. I told you he could even find the wavelength. Because
finding the wavelength just doesn't mean much. I mean, as an argument, it's not surprising that you'd be able to find the wavelength, because the wavelength would have much to do with how it diffracts. So obviously, depending on the wavelength, it's going to decide the point at which it diffracts. So yes, blue light will diffract at a different point because it'll diffract a different percentage when it interacts with an electron. So the more energy the particle has when it hits the electron, the more or less angled it's going to be in the diffraction. So yes, this pattern gets tighter and looser depending on the frequency of the light. Not a surprise.
And it's a simple matter of geometry to see where you got to go for two guys to cancel.
Right, you don't have to do any of that where they got to go to cancel stuff. All you have to do is figure out that there's an angle of diffraction, and with Newton's rings you already know this. You can tell the frequency of the light from Newton's rings also, because the pattern gets tighter, different. It recycles at a faster rate with blue light than it would with red light.
Then once you know that angle, you know where on the screen you will get a minimum or a maximum. He got the wavelength, he didn't know what was doing it, he didn't know it was electromagnetic, but you can
He didn't know it was electromagnetic. You don't know that either. You don't have any evidence that a photon has anything electro or magnetic about it until it hits an electron. Then it has something electric or magnetic. But there's no evidence that a photon has any magnetic or electric component whatsoever.
Hit the wavelength. So interference is a hallmark of waves.
There we go. Interference is a hallmark of waves. So the reason why he's not using the single slit experiment or pointing out Newton's rings is because that's an interference pattern. Now, he'll say it's caused by diffraction. What's the difference? It's an interference pattern. So again, in Newton's time, they couldn't be decisive. They didn't say Newton's rings proves the photons are waves. Did they do that? No. And so why are you doing it now? I mean, if Newton's rings wasn't evidence of waves, why is this nonsense evidence of waves? Oh, that's right. No reason. No rational reason.
Any wave will do interference. Water will do the same thing.
Now, it won't in the single slit water experiment. It won't do anything similar to what light does. Not a single thing similar. Nothing whatsoever like it at all. Just nothing like it at all. Nothing like it at all. You can't use single slit light as opposed to single slit water waves and say, look, they look the same, because they don't. Nothing similar. So you have one experiment where there's similarity and one experiment where there's dissimilarity. And what should you do? What they've chosen to do is, let's just pretend that other experiment didn't happen. And that's all they've done.
For example, this is your beach house. You got some oceanfront property. This is a little lagoon, and you have a wall to keep the ocean waves out of your mansion. And then suddenly, one day, there is a break in the wall.
Right, and so he's just again using a water wave example that's not applicable to light, and there's no evidence that it's applicable. They haven't done this experiment with light either. So
break in the wall, the waves start coming in, and you're having a little boat here, trying to get some rest. Boat starts jumping up and down because of the waves. So you have two options.
So again, he's pointing out at least that, well, there's no pointing it. There's no pointing it out. I'll just let him finish.
One option is to go and try to plug that thing But let's say you got no brakes, no motor, no time, no nothing. You just got a sledgehammer. What you can do, you can make another hole. If this water waves are a definite wavelength, only in that case, you can make another hole for these to add up to zero where you want. Similarly, if you don't like the music your roommate's playing,
Right, and it's true, but like your boat would also have to be in the right position because it's a narrow place that it's zero. It won't be zero for a very big space of distance. So, it might not help you. Because it's going to be even worse in the sense that if you do cross more than one of those interference lines, now the fluctuation between the two, the sine wave is twice as high. So now the high will be twice as high. So the boat will rock even more. It'll be more disturbed than the original disturbance. So you have to stay within the tiny distance where the low is a constant low. But anyway, there's no evidence that that's applicable to light. So they haven't done this boat experiment. They haven't done this experiment where they have a opening and then they bash another opening and create a low spot. They haven't done that. So, until they do, prove it.
if you can manufacture the same music with the phase shift of pi, you can add them together, you get zero. But you got to figure out what the roommate's about.
Right. So I would argue there's no experiments that demonstrate that this pattern is an interference pattern. So there's no evidence that this is necessary at all, that there's anything in this area that's combining and creating the end result here. My argument is what I would claim is happening, and what I think the evidence at minimum says, is the event happens here at the slits. There's no pattern of interference, and it's decided based on where the photon goes here, where it's going to end up here. And it ends up in these patterns because there's an electric potential between these surfaces, and the photons are hitting electrons that are changing their destiny because the photons aren't moving in straight lines, because they're in an electric field, because they're next to a slit, and the slit has a curved field line, and the electrons are moving on the field line. They can't move off the field lines. So when they get accelerated, they accelerate crooked, and then they readmit the photon at a new angle. So I've already sort of explained that. So I don't know if I want to go too deep into this. Gets into the Einstein argument about the particle. Well, let's do a little more.
What to do and be synchronous with a person, but get a wavelength of pi. I mean, a phase shift of pi. So you can cancel waves. That's the idea behind all kinds of noise cancellation. But you got to know the exact phase of the one signal that you're trying to cancel.
Right. So there's no evidence that a photon has gotten canceled, and what there is, I think, is absolutely proven, is that the amount of stuff hitting this is the same as the amount that left here. So you didn't really cancel anything. You just changed where it showed up.
All right, so everything looks good for Maxwell till you start doing the following experiment. You make the source of light, whatever it is, dimmer and dimmer. Okay? So you may not be able to turn down the brightness. Maybe you can, maybe you cannot. But you can imagine moving the source further and further back. Okay? You move it further and further back, we know the energy falls like 1 over r squared. So you can make it weak. So here's what we try to do. We put a new photographic film. We take the light source way back. Then we wait for something to happen. We come the next morning, we find there's a very faint pattern that's taken place overnight, because the film got exposed all through the night. Now we can see a faint pattern. Then you go and turn it down even more. Then you come back the next day, you look at the film, you find no pattern, just two or...
Well, again, this is this argument about the fact that it's quantizable. It's a discrete corpuscle, a discrete amount of energy that arrives at the target. And unlike a wave, it's not spread out in any way. So it's a little tiny point where all the energy goes, which doesn't sound like a wave. But obviously, the wave they have of these things called photons wouldn't make any sense in the way they're describing it if they were actual waves anyway. They obviously couldn't travel across space without spreading if they were actual waves. So clearly they're not in any way like a wave, except they make a pattern, okay, on, off, on, off. So the only reason why they're calling them a wave-like thing is because they make a pattern and because they have a frequency. And they're basically arguing that almost everything that has a frequency somehow has to be traveling through a medium or something like that, which is nonsensical, and it's not a rational rule. Yeah, it's not a rational rule. Things can come at frequency. Frequency and wave mechanics are not in any way necessarily tied together. Waves are dependent on wavelength and frequency, but that dependency doesn't mean it owns the property. The property exists without a medium. Bullets, for example.
These spots which are being exposed. If you look at the screen, so let me show you this view of the screen. Normally you will have bright and dark patterns on the back wall if you turn on a powerful light, but I'm telling you, if you have a really weak source, you just find that got exposed, that got exposed, and that got exposed. That's it. Only 3 points of the film are exposed. And that is very strange, because if light is a wave, no matter how weak it is, it should hit the entire screen. It cannot hit certain parts of it. Waves don't hit certain parts of it. In fact, how can it hit just one? For example, if you make it weak enough, you can have a situation where in the whole day you just get one hit. So something is hitting the screen and it's not a wave, because the wave is spread out over its full transverse dimension, but this is hitting 1 point on the screen. So you make further observations and you find out that what happens here is that a certain amount of momentum and energy are delivered during that hit. If you could measure the recoil of that film, you will find it gets hit, and the momentum you get per hit looks like h bar times k. I'll tell you what it means. This is 2 pi h over lambda. But lambda is your wavelength. H is a new constant called the Planck's constant. And it's bound.
Right, so they're just creating something to create the quanta, some amount of something. Whether you call them kelvins or calories, or that's where it all goes south anyway. So it almost doesn't matter what they have as this h, because that's just a contrivance. So it's the real relationship is the wavelength to 2 pi. So 2 pi divided by the wavelength gives you the proportion of you could just use it as a proportional number. You could just establish it as a percentage of 1 and leave it at that, a decimal.
Value is 6.6 times 10 to the minus 34 joule seconds.
Right, I mean, there's really not much point in an energy quanta that small. Why bother with it when you just need the relative comparisons? Is it twice as big? Is it 3 times as big? That'll tell you how many photons it is, technically.
You also find every time you get a hit here, there's a certain energy deposited here. And the energy deposited here happens to be h bar omega, where omega, as you know, is 2 pi f. So here's what I'm telling you. If you send light of a known frequency, a known wavelength, and you make it extremely dim, and you put a photographic plate and you wait till something happens, what happens is not a thin blur over the whole screen. What happens is a hit at one location. And what comes to that location seems to be a bundle of energy and momentum, i.e. a particle.
I.e. a force. So, yeah, light's a force. That's what happens. The same thing happens when the electromagnetic force hits an electron. It's a real momentum. So again, they just haven't, the same thing happens when you move because of gravity. All of it's the same thing, and it's quantizable, and it can be reduced. So I don't want to get into the other video, the other lecture series I'm doing is, alright, so they're getting into all this relativity stuff, and it's all so much dependent, again, on how they understand what a photon is. So if you thought of a photon as something emitted, and then understood that for it to have a frequency, there has to be a distance between them, so they're bullets. And then you could sort of understand that, say if I have a radio tower, and it produces a bunch of photons, that is a wave front, the beginning of a wave. It's not going to be for another 3 miles maybe in terms of time, 3 miles at the speed of light, before that antenna swings back again for the second wave, which defines the frequency. And so in a sense, those photons, the first wave front that left, if there's no second wave, it's like they don't exist. It's their momentum, their energy, all of this stuff won't be realized because no electron will feel it. It won't see it. It'll pass unaffecting it. It'll go through it without any accelerating of the electrons. But if it has the frequency, then it will accelerate the electron. So if it pushes them twice, then it pushes the electron enough to make it roll, so to speak. It's enough energy to cause the change to take place. And so he's going to be getting into that when he starts talking about Einstein and the the photoelectric effect. And it's the same idea, where if you understand that light's being produced, and for it to be received by an electron, it does have to come at a frequency. If there's no frequency, it's neither radio waves nor, say, cosmic rays. It can't be realized as something because there's only energy passing through rather than energy absorbed. And that's the rule of matter. So matter, electrons, need to be pushed twice. That's what defines a force that's effective, is something that pushes twice. Or it goes from high to low, high to low, high to low, vibrates it. So it pushes it, lets it rebound, and then pushes again, something like that. Or pushes and then pushes again before it rebounds. That's the question. But anyway, so it does pose a question that I haven't thought through yet. But radio waves sort of does give you an indication that maybe there's no need for the quanta to necessarily interact with the same electron. They just have to interact with a group of electrons magnetically connected to each other. So it doesn't matter which particular electron absorbs the energy, it just matters that the group absorbs the energy, and then one electron will be set free. So all of the energy can be absorbed and just one thing will pop out of it, kind of argument. Because of a tightening of the group, you could even say it's pushing it out because it tightens, and a tightness means something has to give, and there's always a give point. So it's like anything breaking, like a stick. You could bend a stick and it's going to break it at some weak point. It's not going to break everywhere. It's going to break in one place. And photons are doing maybe something similar to the stick. They're bending, they're tensing a group of electrons, and that's going to create one electron that's going to have more energy than the others and pop free. And that'll be your electron that'll create your new photon. At probably a different frequency than the one that came in. And maybe at a different direction than the one that came in. Diffraction. But anyway, so it does make one wonder whether what kind of distances up down kind of horizontal, like bullet A is here and then bullet B is down here. Okay, so how close they have to be to each other to be received as two bullets and to be understood as a frequency between events. So that is kind of an interesting question. Clearly with light from a distant object, you wouldn't be able to resolve what it looks like or where it is very well if there was a great deal of distance off there on the perpendicular to their movement. If there was a great deal of difference between their positions, it wouldn't be very likely that you could see them as a single point, but what we see as a single point is so huge compared to the actual size of photons that maybe it's not an issue just because we never resolve anything that fine. Yeah, so so radio waves are so the thing that's really being detected is merely the occurrence of a particular polarization, and that's sort of what you get with radio waves. It's a group of quanta of a particular polarization, and then there's another group of quanta at that particular polarization, and any overlap between them or any consistency between them is just incidental, any on the same path. And that might be why radio waves don't have the same kind of resolution power. You can't see with radio waves any kind of detail, is because they're likely not on the same trajectory. They're misaligned enough to create too much noise for you to be able to see with them. See detail. Fine detail. Okay. So yeah, it's not so much the wavelength that corrupts them as a mechanism for seeing, as it is the fact that they're created in volume, not necessarily by the same electron, by the same mechanism. Their origin isn't exactly the same. That's a good way to put it. The first quanta and the second quanta their origin isn't the same point. And then that gets you to this relativity argument in the sense of what's redshift then. And so they use experiments. Like I said, this is what I'll talk about in the other video whenever I decide to get back on that relativity subject. Might be tomorrow night. We'll see how things go. But there's just so many ways you can look at this thing about what they attempt to argue almost is that distance is stretching the light, and that's causing redshift. And it has nothing to do with the distance the light travels. It has to do with the source and the receiver. If the source is moving, you can sort of understand that if you understand light to have two components, a beginning and an end even. So even if you thought of it as a wave and it had a beginning and an end of the sine wave, but obviously if you thought of it as particles, particle and particle, front particle, end particle, which is the beginning particle of the next wave, so to speak, but regardless, that you could sort of understand that if something's moving fast, it will produce a first particle, and then by the time it produces the second, the gun will have moved forward, and it's compressing the distance between the bullets. So if the gun usually fires 1 bullet a second, and I move the gun in the direction it's firing, it will appear to the target, okay, as if the gun was firing more often than once a second by exactly the distance it's approaching. So whatever percentage of the speed of light it's moving will be the increase in the frequency produced. And that's all that really matters. So it's how the emitter and how the receiver are moving that will define redshift. So if the emitter is moving towards you, then the light you're going to see is going to be compressed in its frequency. The bullets are going to come more regular because it's shortening the distance between the bullets. Okay, not over the length that the thing moves, but at its origin. So it's red shifted from the very moment it's created. I mean, it's blue shifted. In the same argument, if I'm receiving light and I'm moving away, I'm going to stretch out the receiving. I'm going to catch the first beginning of the wave, quote unquote, and then I'm going to move before the end of the wave gets to my glove. And so I've lengthened the amount of time it took the wave, first hit, second hit, to get to my glove. But I've done that. I've distorted the reality by moving. So the reality didn't change, the light didn't change. The light was exactly what it was admitted as, and I changed it by receiving it wrong. So you can either produce light that's redshifted, and then you can receive, which means you can receive light by redshifting it further. So you always have to be aware of that combination. So in an experiment like an interferometer, you would have to move it very fast for you to go so fast that the emitter and receiver aren't compensating for each other. Because technically they would be doing that in most circumstances. You move the emitter, which means you blue shifted it, the light. Well, the emitter and the receiver are both moving in the same direction, sorry, because of the mirror. And then you're moving the receiver, which is further blue shifting, because you're moving into the light coming back. But yeah, that change in distance is a fraction at small scale. So you need a very large device moving very fast to be able to see those changes. To create changes that be visible. Better way to say it. Yeah, so that's probably it. Like I said, I don't want to get too deep into that. But I guess the key point is you know you're never in the absolute frame if you can imagine that if I move something the speed of light and there's no more experiment, in the sense it doesn't matter how, if I'm moving the speed of light and I'm producing light forward, it's obvious I can't produce light that can go ahead of me because it would have to go faster than the speed of light. So automatically I've made it irrelevant where the target is, in the sense that neither one of us can get to the target by that definition. If there was some sort of frame where light was still moving the speed of light, no matter what, it clearly can't move the speed of light if I'm moving the speed of light. It can't move is the point. It can't proceed. It can't advance. But like I said, it's a moot question because you can't create any matter that can be moved at the speed of light. So it's a paradox you'll never realize. But everything short of that will have an effect. It's just whether you can measure the effect. And it's pretty much impossible to measure it because your measuring device is going to be doing the same thing the broken instrument is doing. So what are you going to measure it with? What are you going to use to time the difference? And you won't have a clock that works. Alright, well, I didn't want to get into that. But I don't know if I need to